So in this final segment, I want to give a brief introduction to statistical methods to machine translation. And statistical methods will be the focus of the next few lectures of this class. So here's the basic idea. A key observation is that so-called parallel corpora are available in many language pairs. So a parallel corpus, let's say for English and French, consists of a set of example translations. So each element of the corpus is an English sentence paired with some French sentence. So we have sentence pairs where each of these sentences in English has the associated translation in French. So we're basically going to treat translation as a supervised learning problem where we have EF examples. E is an English sentence and F is a French sentence, assuming we're trying to build a translation system from English to French or from French to English. And we might have many thousands of example translations. So it turns out that these kind of corpora exist across many language pairs. So one classic example is from early work at IBM, really the seminal work in this area of translation. They used a corpus called the Canadian Hansards. So these are proceedings of the Canadian Parliament. So anything which is said in the Canadian Parliament is written down in both English and French. And so actually we have millions of example translations between English and French. But many other language pairs have these resources. For example, the Europol corpus is a corpus drawn from the European Parliament, and it contains, I think, 15 or 20 European languages, where again we have translations into all of these different languages simultaneously. So the first statistical machine translation systems came about in the early 1990s, largely due to these researchers at IBM. And as I said, the basic idea is to take some example set of translations and then to try to learn a statistical model which, given a new sentence in, say, French, will translate it into English. This, on the surface, is sort of a radical and rather preposterous view. It's completely different from the rule-based approaches which had been developed prior to the early 1990s. But it actually has been a highly successful approach, and over the last 10 or 20 years there's been a huge amount of research on statistical machine translation, and it's gotten to the point where commercial systems such as Google Translate use precisely these technologies. The idea actually is an old one. It goes back to Warren Weaver just after the Second World War, who suggested applying statistical and methods from cryptography to translation. Actually, if we go to the next slide, here's a quote. So here's a quote from Warren Weaver in 1949 in a letter to Norbert Wiener. So he was spurred on by great successes in the Second World War, where statistical methods had been used to decrypt encrypted messages. And so he says the following: one naturally wonders if the problem of translation could conceivably be treated as a problem in cryptography. When I look at an article in Russian, I say this is really written in English, but it's been coded in some strange symbols. I will now proceed to decode. So Warren Weaver sort of had this preposterous idea of using statistical or cryptographic methods to try to perform a translation. So let's talk a little bit more about how the IBM researchers actually envisioned this translation process. And their idea was to apply the noisy channel model, which we saw in the lectures on tagging models. So their idea was to apply the noisy channel model to translation. So by convention, let's just assume that our goal is to build a translation system from French into English. So we want something which maps some French sentence F to some English sentence E. And you know, a natural way to try to do this is to try to build a conditional model, PE given F. So we have with some French sentence F, if we consider every possible sentence in English in turn, very large set of course, an infinite set of sentences, we assume that each of these sentences has a probability E of f, which is the conditional probability, given that I'm translating f, that E will be the output. Now, in a noisy channel model, we're again going to use a generative model, and we're going to use Bayes' rule to kind of flip this problem around. So here's how this goes. A noisy channel model for translation is going to have two components. So P of E is a language model. So this will assign probabilities to sentences. For example, like the dog laughs. Stop. And this, for example, might very well be a trigram language model, exactly as we saw in the very first week of the class. Okay, so this is a model that we can learn from very large amounts of English data alone. The second part of the model is what's called the translation model, and this is a model of P of f given E. Notice that this is reversed from the direction here, and this is what we often see with the noisy channel model. So Pf given E for any English sentence, for example, the dog laughs, if we consider all possible French sentences, so again an infinite set, we're going to have a model Pf given E for each French sentence conditioned on the English sentence. Okay, this model is going to be estimated from a set of translation examples. Okay, so this is going to be estimated from our bilingual corpus, parallel corpus. Okay, as we saw before with the noisy channel model, if we have these two models, we can actually derive P given F using Bayes' rule. So by the usual rules of probability, this is PEF over F, and this is PE times P of F given E, divided by, and here I have a sum over all English sentences of PE times P of F given E. Okay, so given a new French sentence F, we are going to output the most likely translation under the model, and so that means we're going to search for the sentence E that maximizes this conditional probability. And now I can plug this formula in here, and notice that this denominator, it's constant with respect to the English sentence we're searching over, and so this constant term isn't needed when we're considering the argmax. We saw exactly the same trick when we saw noisy channel models for hidden Markov models earlier in this class. So we end up with the following problem. So remember, again, our problem is to take some French sentence F and to produce some translation E. To do this, we're going to search for the sentence E that maximizes the product of two terms. This term is a language model term. It's the prior probability of the English sentence E, and the second term is a conditional probability, the probability of the French sentence F given the English sentence E. Of course, we've seen how we can build a language model using a trigram model. Over the next few lectures, we'll see how we can build models Pf given E, these translation models. That is going to be the critical new component of these translation systems. So a few more notes about the noisy channel model. So as I said, this language model can be estimated from any data, and actually we don't need a parallel corpus to estimate the parameters of the language model. So that means we can actually leverage potentially very, very large quantities of text in English alone. This translation model is trained from a parallel corpus consisting of French-English sentence pairs. Notice that even though our goal is to translate from French to English, because we've used the noisy channel model, we estimate P of F given E. Okay, so things are flipped. The translation model is in a sense backwards. One big advantage of this is that we now have a model that makes use of a language model over English sentences, and this gives us a very strong source of information about which sentences are likely or grammatical or fluent on the English side, and that can make up for a lot of deficiencies in the translation model. Okay. Next in this class we'll talk about how to build this model of F given E, And then finally, we're going to be left with this problem of, for a given French sentence F, finding the English sentence that maximizes the product of these terms. This is also a very challenging problem. We're searching over a very large set of possible translations, and so we'll talk a lot about this problem a little later in the class. So here's an example of the noisy channel approach from a tutorial by Philip Cohen and Kevin Knight. And so imagine we're trying to translate, in this case, from Spanish into English. There are many, many possible translations, many possible English sentences. And what we've shown here is a few possibilities. And in each case, we've shown the conditional probability of the Spanish given the English under the translation model. Okay, so we might get these various terms here. And notice again that we have P S given E here. We do not have P E given S. Okay, so this part of the translation model is actually backwards from what we really need. And so that's one component of the model. When I evaluate the probability of these different translations, this is one component that I take into account, P of S given E. And notice that if we just use this part of the model alone, we would actually come out with this translation, which is a pretty bad translation. But here's the full model, and notice that now, to evaluate the probability of each of these English alternatives, I actually take the product of two terms, P of S given E times P of E. So this is now the model under a trigram language model of the English sentence. So for each of these English sentences, I can calculate its probability under a trigram language model. And some of these sentences, of course, are much more likely than others. In particular, this sentence here is much more likely than these other sentences. And when we multiply together these two terms, you'll find out that the highest probability translation is actually this one. So at a high level, the important point here is that to evaluate the plausibility of each of these examples as a translation for this input, we multiply together two things. Firstly, P of E, which is the prior probability under a language model of seeing the sentence in English. And secondly, P of S given E, which is the probability of seeing the Spanish sentence, given that we have this English sentence underlying the process.